For Algebra 2 with trig, we're looking at section 5.8. We're looking at working with graphing polynomial functions that are going to be in an intercept format. This first gray section is giving you some notes. The k value, this is different than your h and k, but your k value is considered to be a 0 of the polynomial. If k is a 0 of your polynomial, then x minus k is going to be a factor. And then k would be considered to be the solution. And it's the solution when the function equals 0. These solutions are going to be X-Intercepts. Let's try and let's talk about how to graph these. I'm going to graph these without our table at all. What we're going to look at in intercept form is that we have x plus 2. So using the zero product property, we get x is negative 2. So on our graph, at x is negative 2, I know I'm going to have a 0. I have x minus 1 is also going to equal 0. So add 1 to both sides. I'm going to get a 0 when x is 1. So those are the points that I know of for sure. These intercepts are negative 2 comma 0 and at 1 comma 0. Now instead of doing the graph, we're going to use the end behavior to help us determine how this graph is laid out. Notice what type of function this is. We see two x's, two sets of parentheses, so it's kind of like a quadratic. But what's different is that this set of parentheses is squared. So the squared is going to make this an x squared. So really it would be x squared minus 2x plus 1. But that would have to be multiplied over here to this x. So this is really multiplying to become an x cubed problem. This is an odd degree. So if it's an odd degree, then we know that it's going to be going in opposite directions. And when the leading coefficient is negative, it's going to be dropping to the right. We know that for sure because it has a negative for your leading coefficient. Now, because it's an odd degree, there would actually be x cubed if you multiplied this all out. Then we know this has to go in opposite directions. There is no reason to test points to determine that. From this point, it's kind of tricky. Take a look at what we have. We only have two intercepts. So one of those intercepts has to actually count for 2. Something weird's happening. So those two are going to, when x is 1, x minus 1 squared, that means this is happening twice. That's called a double 0. At every double 0, it's going to bounce. It's going to touch the x-axis and it's going to start coming back down. And then we know that it would come down for a while, curve back up, and go through where x is negative 2. We know it goes straight through at negative 2 because the x plus 2 is not squared. It's just x plus 2. It happens once. This x minus 1 is happening twice. So something weird's happening there. It's called a double 0, and the graph will always bounce at that location. So we'll write our equation as x plus 2, x minus 1. Don't forget your square over that. In determining our end behavior, we know that the function has 3 factors. It has x plus 2, x minus 1, and x minus 1 again. We know that the leading coefficient is going to be a negative. the leading coefficient has a constant of -1. So when we're determining what degree of a function it is, we can see that this would be a cubic function with a negative leading coefficient. We know it's cubic because there's 3 factors. X times x times x is going to make it a cubic function. When we look to the left, we know that it increases. When we look to the right, we see that it decreases. It approaches negative infinity. We were able to graph this. We did not need the table. The table could have helped us if we were looking to see just how low this was going to curve. I just approximated it. It might actually go farther down. We're not worried about just how low it becomes. We'll talk about how to do that with your calculator. If you were really concerned about that, you could plug in values between your 2 intercepts to see just how low it became. But those numbers that you got still wouldn't be the lowest spot. It could still land further down in between any 2 that you tested. So for our second equation, we're going to set the first parentheses to 0, the second parentheses to 0, and the third parentheses to 0. So this graph is going to have 3 zeros for the function. We see again that there's 3 parentheses, so this would be a cubic equation. -2, 0, 1, 0, and 3, 0. We see that it's a leading coefficient. It happens to be a quarter, but it's positive. So it's a positive leading coefficient, so I know it's going to increase to the right. Therefore, it has to decrease as we look to the left. And in between, do we have any factors that are squared? We look here and none of these are squared. We have 3 separate ones. So it's going to increase and fall back down, then it's going to decrease until it curves back up to finish off towards positive infinity. We write our equation as 0.25 x plus 2, x minus 1, and x minus 3. We can determine the end behavior. We see that the function has 3 factors, and the form is going to be x minus k and a constant factor of 0.25. Because there's 3 factors, this is going to be a cubic function, and it has a positive leading coefficient. When we look to the left, the graph is decreasing, it's approaching negative infinity, and when we look to the right, the graph's going up, so it's approaching positive infinity. On our next page, we're going to look at the number of turning points. I've made a reference to some of this already, but thinking about a linear equation, which would be x to the first power, it has no x-intercepts. Think about a parabola, which would be something like an x squared type function. It has 1 turning point. A cubic equation is going to have something with x cubed. It could cross the x-axis up to 3 times, but it's only going to have 2 turning points. So the graph of every polynomial function, and we'll say that it has n as a degree, the most turning points it's going to have is 1 less than that. If a polynomial function has n distinct zeros, then it has exactly n minus 1 turning points. So you can look at the zeros and we can tell that the turning points would have to be one less than that. We're going to start with our equation. So in your graphing calculator, you'll type in x cubed minus 4x squared plus 6. We can graph that. You might need to change your window back to normal, so we'll hit zoom number 6, and it produces our cubic equation, which has 2 turning points. It's crossing the x-axis 3 times. What we're going to look for is the number of x-intercepts. We have 3 x-intercepts. We're going to use our calculator to identify just where those are at. You need to notice that our x-intercept is in these exact 3 locations. You need to be aware of their location. So to find the actual value there, we're going to go second trace, which is the calc. We're looking for the 0 of the function. So that's number 2. It's asking us a question, the left bound. So we need to be left of the number that we're looking for. So if we're looking for this value here, we need to be to the left of it, which is anywhere below this x-axis. And we're going to hit enter. Now it asks us for the right bound. So we're going to arrow over to the right, anywhere to the right, go as far as you wish. We need to be to the right of this x-intercept, and we hit enter. Now guess is only used for if there's more than one answer in between the window that you just gave it. Or just to make things safe, you can always get as close as you can and hit enter. So that gives us one of the zeros to be negative 1.086. To look for the second 0, we're going to do the exact same thing. We have to go to second trace, which is the calc, down to 0. We need to be to the left of our 0, anywhere to the left, hit enter. The right bound, we need to be anywhere to the right. We're to the right of this x-intercept. And then guess is getting anywhere close to where it's at. So this is going to give us another location of 1.57. We could round that up to a 2. Then our third one, it's going to start with the left bound, so we have to be to the left of our intercept, anywhere to the right of that intercept. And then for the guess, you can get as close as you can, and it tells us that we're going to get an x equals 3.514. Now look what it says for the y value. It says that this y value is 2e negative 12. That's actually telling us that we're going to go 12 decimal spots to the left. From 2 and then 12 spots to the left, that's going to give us 0.000000002. So essentially that is the number 0. It's actually exactly 0. The way the calculator will determine where this is at, it comes up with a number that's super close. The E stands for exponent. It is not standing for error. We're going to look for local maximums. The local maximum on your graph, if you notice, it goes up forever, so there's not a total maximum. There's a local maximum. So we'll go to second trace again. We'll go to maximum, and it's asking you those same set of questions. Get to the left of the maximum. Well, I know the maximum is right up here. because it's curves and it changes its direction and it starts to come back down. So we're going to go to the left of that because we're looking for the left bound. Then we need to go to the right of that because we're looking for the right bound, and it says to guess. Well, we've narrowed our window down enough, but we could also get right on it as close as we think the maximum would be, and it tells us that we have this, again, negative 2.5 e to the negative 6. So essentially that would be 0.00000025, which is 0. And our y-intercept would be 6. It's just the process that the calculator used to determine where the intercept is. Sometimes this will give you an extremely small number, which is what's happening here, is actually the real number of 0. We're looking for the local minimum. So where on the graph would a local minimum be? We can tell the graph goes down forever, so there's no real minimum, but a local minimum would be the low point where it goes down and then curves back up. That's our local minimum. So we're going to go to second calc. We'll go down to minimum. We need to be to the left of that, and then to the right. And your guess is to be as close as you can in between that. So we have a local minimum of 2.66, negative 3.48. Notice that the graph of the function has 3 x-intercepts and it has 2 turning points. We see the x-intercepts where the graph crosses the x-axis, and we see the turning points by how it increases to decreases. That's one turning point. It decreases, then increases. That's your second turning point. Now we can look at the equation, just to practice a few more. So if you go back to y equals, type in your x caret 4, got an arrow to get off of that, plus 3x caret 3 minus x squared minus 4x minus 5. When we graph that, we see this funny shape. We see that it's pointing in the same direction. That happens for all even degrees, so we're not surprised by that. This is only touching the x-axis twice, so we only have 2 x-intercepts to find. So we go to second trace, down to 0. We need to be to the left of the 0 we're going to look for. So right here is a 0. We need to be to the left of it, so that's going to be anywhere above it. Then we need to be to the right of it, right bound, so that's anywhere below the 0. And then we can get as close as we can, and either one of those is pretty much as close as we can. So we hit enter, and we have an x-intercept at negative 3.07. We have another 0 on this side of the graph. So we'll curve over. Remember, we want to stay to the left of it, so that's anywhere below it in this case. And then to the right. And you can get as close as you can, would be fine. And hit enter. And our second x-intercept is 1.42. Your local maximums. Where on your graph would a local maximum be? It would be at the curve. Here would be your local max. There's not a complete max because the graphs go up forever. But your local max, hit second, trace, look for your maximum. We need to be to the left of where you think that location is at. You need to be aware on the graph where this is. So we need to be to the left of it. Anywhere to the left of it is fine. Then you need to be anywhere to the right of it. And then back towards about where you think it might be. And we have a maximum at negative 0.6495 and negative 3.468. Any number of points. The notes say to round to the nearest hundredth, so that's really just 2 points. So you could call this negative 0.65, and this would become negative 3.47. That's fine. Local minimums would be the low point. So second trace, we go to minimum. You need to be to the left of where you think your minimum is located. That's going to be down here, so that's to the left of it. That's to the right of where our minimum is going to be located. And you can just start heading down to about where it would be. And we have a local minimum at negative 2.28 and negative 9.61. That's the XY location of your local minimum. Then we have another local minimum on this side of the graph. So we need to be to the left of it, and then we need to be to the right of our local minimum. Then you can get as close as you want to get. And that gives us a second point at 0.68 and at negative 7.03. Those are X-intercepts, and those are minimums and maximums, local mins and maxes. On our next problem, we're finding the X-intercepts, the local maximums and local minimums. So we type in our equation. And we watch that our cubic equation could have a maximum of 3 X-intercepts. This one only has 1. It has a maximum and a minimum. So our 0, we need to get to the left bound. So that means to the left of the intercept. We need to get to the right of the X-intercept. And then the guess means that we should get as close to it as we can. So our X-intercept is X equals negative 3.07. We have a local maximum where it curves up and then begins to go back down. That's our local maximum. So we have to be to the left bound, the left side of that. Move to the right side of where we see that our maximum would be located. And then you can get close to your maximum. So our local maximum is at negative 1.724.13. We're rounding to the nearest hundredth. Our local minimum, so we're going to use number 3. We're at second trace. We're at our minimum. And our left bound, we're to the left side of our intercept. We're to the right side of our intercept. And this is at 0.39, 1.79. Next, we're going to look at this piece of cardboard. It's 20 inches wide by 16 inches the length and width of 20 and 16. We're going to cut into it so that we can fold up the edges. we're going to cut in the same amount, so it's a length of x. How much should we fold up the box, essentially what we're cutting into it so we can fold it? How far in should we cut it? That's what we're trying to determine. We're trying to maximize the volume. So we know that our length is going to be a total of 20, not counting the two x amounts that'll get folded up. So this width is going to be 20 minus the two x's. Those parts of the 20 are going to be coming upwards, so the width will be smaller than 20. So length times width times height is what volume is. Well, we're going to have 20 minus 2x. That's what our length is. Our width is going to be 16 minus the 2x's. And then our height is going to be what the x is. When you fold that up, it's going to be at a height of x. And what we want to do is figure out what our volume is. So, the way that we've been looking at doing this problem, you could turn this into standard form by multiplying this all together. So we would FOIL this. We've got 2 times 16 is 32, so 20 times that is 320. Negative 40x, negative 32x, positive 4x squared, with our x still on the outside. And we're going to have 4x cubed when we multiply here. This is going to become negative 72 x squared, because our x, this is negative 72x times x makes it x squared, and then here that's going to be a positive 320x. So that's going to be the volume. So we'll take our calculator. We'll type in our 4x cubed minus 72x squared. Let's try that again. 4x cubed, then you got to arrow over to get off of the exponent, minus 72x squared plus 320x. Don't forget that x. So what they're suggesting here is that we use 0 to 8 for our x's. So we go to window. Your minimum x that it's going to show is 0. Our maximum x is 8. Your minimum y is 0. And your maximum is 500. They're suggesting us to fix our window so we can see the graph correctly. So we want to know if we even zoom back more, you could see more of the parabola, or more of the cubic equation. But we've zoomed in to the window that they suggested. We know that our maximum amount can be found by doing a local max test. So if that's going to be about where the maximum's at, we need to be to the left bound of that, to the left side of that. Then we need to be to the right side of that. And then guess is only there for if you have more than one answer inside your window, but sometimes it's a good idea just to get close to it anyway. So that's where our maximum. Okay, the local max is 2.94 and that'll give us a volume of 420.11. That's what the local maximum is going to give us. So how long should the cuts be? We're going to have a cut of about 3 inches. And over here, we're going to have a volume that is about 420 inches cubed. So the finished dimensions, the length, which is 20 minus 2x, is going to be 20 minus 2 times 3, which is 20 minus 6, 14 inches. The width, 16 minus 2x, which is 16 minus 2 times 3, 16 minus 6, which is 10 inches. And then the height, which is just x, which is approximately our 3. So we get 3 inches. So our length, width, and height of our maximum volume. If you come back and look at your graph, if you take your window, now let's look a little bit farther. Let's look to the left, 100. Let's look to the right, 100. Let's look down, negative 100. See if we can see more of our graph this time. So you see we're really zoomed in. So let's bring that way back. Just trying to give you more of a picture of what's happening with this. Zoom in some more. Okay, you start to see what's happening with the parabola. There it's curving. Okay, so you can see that it's crossing 3 times, but you have one local maximum, and that's the calculation that we just found.